Okay, good morning, everybody. So I think next week you have a quiz, or your first test in this course. It's going to be in this room. It is written, happens during lecture time. The topics on the first quiz go up to and including the floating point lecture, and that's it. So you don't need to know about lists or collections otherwise. You just need to know about, basically you need to know the basic Java language, how to use arrays, strings, and do some simple floating point error analysis. And that'll be it. So it's a 50-minute quiz. Yeah, and I guess that's all there is to say about that. So I'll post last term's quiz to OnQ later today or tomorrow. And I'll post the solutions as well. Any questions about the test? Okay. So today's lecture is, the topic of today's lecture is how you organize a Java program, and hopefully we'll start to implement a Java class. Okay, so from your assignments, especially assignment 2, you've already seen what a Java program looks like. Right? So the organization of a typical Java program is a bunch of files, and they're normally just text files. Right, so if you go to Eclipse and you look at assignment 2, and you go to assignment 2, right, over here you can see that in assignment 2, right, there's a bunch of files, right, and each one of those files contains a definition or the implementation of a single class. At the top of each file may be one or none package declarations. So I'll explain exactly what a package is shortly. Right. And then if you're using classes from other packages, you have to import those classes. So there will typically be 0 or more import statements. And then typically there's one class. Now you are allowed to have more than one per file. But typically you only put what's called one top-level class per file. Right? So a top-level class in Java is just a class that's not defined inside of another class. Inside that class, you have some variables that belong to the class. Right? So those are called fields in Java. You also see the term attributes. You might see the term class variable and or instance variable. And those two last things are actually slightly different things. Then you'll see your constructors, 0 or more, and then you'll see your methods, again, 0 or more. Right? So if you go into one of our assignment 2 files, right? So here is, what's this one? This is life 2. Right? So this is the solution for assignment 2, which I'm not going to show you the whole thing. Right? You can see at the top, there's a package declaration. So the class life2 is defined in the package called game of life. Right? Then there's a bunch of import statements. There's the class declaration. So here's our one top-level class. And now this class doesn't have any constructors, but it does have a bunch of methods. Right? And so now we have our 0 or more methods in the class. And every other class in this package is similar. Right? So here's the viewer class that's used, that you use to actually view the that's used to draw the game of life in assignment 2, right? Again, it's in the package game of life. There's an import statement here because we need to use a class that's not defined in the package game of life, right? There's our class. This class has a field, so that's nice, right? So it's actually it actually has a variable defined in this class, right? And then it has a bunch of methods, and so on and so on and so on, right? If the class has a main method, then you can actually run that class as though it were a program. Right? So the viewer class does have a main method. Well, at least it has one on my computer. I don't know if I gave you a main method in the assignment. Right? But that makes a little grid, so that makes a little game of life of size 50 by 50, sets one cell to true, and then draws the grid. Right? If you finished assignment 2, then you know that there's a demo read program that just consists of a main method, and if you run that, you actually get a version of the game of life that runs. So if you ever get it to run, eventually you can end up generating a picture like this. Right? And this thing here will just go on. I think this is configured to go for 1,000 generations. So this will eventually stop. Okay, there's an example of another Java program. Well, this is just a Java class. This is not a full program. Right? So this is just, ignore the content, right? So ignore the code that's in there. What you want to look at is the structure of the program, or of the file, right? So there's a package declaration here, import statement here, class declaration here. This one has a field in it, so this one has an array list as one of its fields, right? That's a constructor, which we'll look at in more detail later this lecture. And then we have a bunch of methods. And it's actually much more complicated than this. So in a typical Java program, there can be many other features, some of which we see in this course and some of which we don't. Right? And so there's just a list of stuff that you might see in a class. Right? If you want to know more about these, click. We'll see later on in the class, right? Later on in the course. Right, so, for example, we'll see classes inside of classes. We won't see. We'll see classes inside of classes, and it looks like that's it for that list there. Right? But a typical Java program can be quite complicated. Okay, so let's start out at the very top. So, what's a package? Right, so, a package is one of Java's mechanisms for modularity. Right? So remember in the last class I told you modularity is one of the pillars of the object model, right? And so packages are one way that that Java uses to organize a program into to organize a program, right? So packages are used to organize classes and other things into what are called namespaces, right? And a namespace is nothing other than a container for names, right? So the reason you use a package is because you want to because a typical program contains many classes. And you want to organize those classes in a way so that your program is easier to understand. Right? So typically what happens is you take classes that are related to one another and you place them into the same package. So the Java standard library, right, puts all of its classes in this package called Java. Right? So when we use the class math, you should know that it's in the package java.lang.math. Right? And when you're using the class array list, it's in the package java.util. Right? A package can contain other packages. Right? And so the package Java contains other packages like lang, util, io, and so on, and so on, and so on. Right? It contains a bunch of other sub-packages. And so there's a package then has what are two different names, right? So a package has its own name, so lang, for example, right? And then it has what's called the fully qualified name, right? So the fully qualified name is just the sequence of all the packages where you find a package strung together using periods, right? So lang is inside the package Java, so its fully qualified package name is java.lang. Util is in the package Java, so its fully qualified name is java.util. Inside a package, you're allowed to put classes and interfaces. Right? So inside Java Lang, you'll find the class string, right? And math and big object. Right? So all of the classes that are considered fundamental to the Java language, they're inside the package java.lang. Right? So just like packages, classes can have fully qualified names. Right? So the name of the class string, or the fully qualified name of the class string, is java.lang.string. Right? So it's just the name of the class with all of its packages attached to it in the front. Right? Now one of the reasons why we use packages is so that your class names are unique. Right? So you can imagine writing a very large Java program. It's probably the case that you're not making your own, that the classes that you're using in your program, not all of them are made by you. So you're going to find other people's code to help you with your program. Right? You can't control what other people are naming their classes. So if someone makes a class called, I don't know, myString, right? And you also have a class called myString, you've now got a problem. Right? So you've now got two classes with the same name, and there's no good way for you to specify which class you're using. Right? So that's where packages help out. If you put your classes into your own packages, right, and then there's a much better chance that your fully qualified class names are unique. Right? So you can go ahead and make a class called string, right, and put it in a package called, in this case, your, right? And now you can use your string class and the Java string class in the same program at the same time, right? You just have to make sure that when you use your string class, you use the fully qualified name, right? And now your class names are all unique. Right? This was a big problem with the programming language called C. So in C, there is no package mechanism, so it's very easy to run into a situation where when you try to build your program, you run into a problem where there's multiple things with the same name. Right? And so this is one of the ways that Java tries to avoid this problem. There's still a problem though. So you can't control what other people are calling their packages. You can make up whatever package name you want. Right? And so how do we guarantee that package names or class names really are, or fully qualified names really are unique? And so the answer is you can't really. But what you're supposed to do is follow a package naming convention. Right? And so the convention that Java uses is that packages should be organized using your domain name in reverse. Right? So domain names, or internet domain names, are unique because they are governed by a central registry. Right? So for example, the computing science domain name is cs.queensu.ca. Right? If I'm creating a package that belongs to the computing science department, then what I'm supposed to do is reverse the order of the domain name. So ca.queensu.cs, right? Which is the package naming convention that you'll find if you look at the source code for the course. I think I have it here, right? So if you look in the source code for the course, you'll see that, right? All the packages begin with ca.queensu.cs and then .CISC124 and then blah, 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 blah. Right? So all of your course notes are organized into separate, all of your course classes are organized into separate packages. Okay, there's something else about the package naming convention, about the packages. So the way when you start to put packages inside of packages, that's actually reflected in the file structure of your Eclipse project. So this is not just true in Eclipse, this is true in general. Right? So when you create a Java program, if you're making packages, then the rule is each package should go into its own directory or folder. Right? So if you go into Eclipse, into your Eclipse project for assignment 2, and if you go into this folder called SRC, right? When you open up that folder, you'll see there's two more folders or two more directories in the SRC directory. Right? There's one called Game of Life and there's one called Princeton. Right? Both of those are packages in assignment 2. Right? So if you go into the Game of Life folder, right, there you'll find your classes. Right? So those are the classes that are inside the Game of Life package. Right? So the package naming structure is reflected in the directory structure of the files. Right? So if you actually had to compile your own Java program by hand, you have to make sure that all of this is true. Otherwise, your program won't compile. The Java compiler won't be able to compile your program. Right? In Eclipse or in a modern IDE, typically these things take care of creating the package structure for you, the directory structure for you. Okay, so what about classes? So classes are just user-defined types. And a class is most often used as a blueprint to make instances of the class, right? So in other words, a class is normally used to make, is used as a blueprint to create objects. So why do we want objects? So why can't we just use classes, I guess is the question, right? So you only have one copy of a class, right? So when we make the class, I don't know, Life2 for assignment 2, there's only one class called Life2, right? When you're using objects, typically you want many objects, right, of the same type. Right? So every object is allowed to have its own copy of all of its non-static fields. Right? So in other words, an object is allowed to have variables, and those variables are independent of every other object. right? So what does that mean? It means every object can have its own state, right? So in other words, every object can represent its own individual or unique thing. Right? So in Java, we say that the state of an object is just the set of current values of all of its fields. Right? So I'm going to make this class. So have we seen point 2? We haven't seen point 2 yet. Okay, so have we seen this class? We've seen this class. We've seen point 2. Right? So remember, point 2 is the class that represents a two-dimensional point having an x and a y coordinate. Right? So you can make multiple point 2 objects all having their own x and y coordinates. Right? So there's a little memory diagram of a bunch of points. Right? So I've got, sorry, right? So P, right, is a reference to a new point 2 object whose coordinates are 1, 2. Right? So when you use new and a constructor to make an object, that object lives somewhere in memory. Right? So that object is right there. Right? I haven't told you this yet, but point 2, the class point 2 down here, right? It has a field called x and it has a field called y. Right? So when you make this point 2 object using new and a constructor, right, what happens is we take the class, right, and we just copy it and plunk it down somewhere in memory. Right? So now I have an object that also has an x and a y coordinate. Right? Now the constructor runs and fills in x and y to be 1 and 2. Right? So that's why there's a 1 and a 2 there. Q is a reference to a new point 2 object whose coordinates are -3 and 8. Right? So when the compiler sees new point 2, right, takes the class, makes a copy of it, right? Constructor runs, fills in the coordinates to -3 and 8. Right? And then finally, R is a reference to a third point 2 object whose coordinates are 5 and 13. Right? So classes are blueprints, right? So that's a blueprint for that object. Right? The constructor, that thing there, is the thing that fills in the actual values of the object. Right? And now you've got 3 separate point 2 objects in memory, right? Each having their own set of coordinates. So when you implement a class, there's many types of classes that you could choose to implement. Most of the classes that we implement in this course are what are called value classes. Right? So a class can represent a value like a name or a color or a mathematical point, right? Or a vector. Right? So examples of value type classes are things like string, integer, and date. Right? There's a class called javautil.date that represents times. Okay, so when you implement a class, right, you have to decide what information does every object need. Right? So for two-dimensional points, it's pretty obvious what every point needs. Right? It needs an x and a y coordinate. So that's not too hard. Right? But when you go to implement more complicated classes, it now becomes, there are more decisions that you have to make to decide how are you going to represent the information that every object needs. Right? So we need to decide what fields should our class have. Right? So let's go ahead and see how we implement this two-dimensional point class. Right? So what fields do I need to represent a point? Right? So one way you could do this, right, is I can make a variable called x and a variable called y. Right? And those will be my x and y coordinates. But that's not the only way to do this, to solve this problem. Right? You could create an array of length 2. Right? And then the first element of the array would represent the x coordinate, and then the second element of the array would represent the y coordinate. Right? And there's other ways you could do it as well. Right? You could use a list if you really wanted to. I don't think there's any other sensible way to do it. Those would probably be the 3 reasonable ways that you might try to do it. Right? So how do you make a class? Well, if you want to, you can put it in a package. Right? So this is the class that's inside of this very long package name. Right? So you make your class, so it's just public class and then the name of the class. Right? Remember, the name of the class should always begin with a capital letter. Right? And now you just add your fields to the class. Right? So what variables does every object need? Well, it needs a double value called x, and it needs a double value called y. Right? When you create your fields, you're allowed to specify the access modifier for the fields. So here I've marked the fields as being private. Right? Now private means that only the class itself can use the fields x and y directly. So if someone makes a point2 object called p, they're not allowed to write p.x to get to that field, right? Because it's private. You actually have 4 choices of access modifiers here. They can be public, they can be protected, and they can have no access modifier. For now, everything's going to be private. Occasionally, if we have a constant, we'll make it public. Right? But in general, you should make your fields of a class private, unless you have some other reason, unless you have a good reason not to. Right? Okay, so that class point2 is what's called a top-level class. So it's a class that's not inside of another class. Right? Every top-level class is allowed to have an access modifier. Right? And that modifier can be either no access modifier, or it can be public. Right? So in other words, that's either public or it's nothing for a top-level class. Right? Most of the classes that we create will be public because we want to use these classes, we want other classes to be able to use that class. Right? If you have no access modifier, then that's what's called package private access. Right? So package private access means that only classes in the same package can see that class. Right? So if we were to strike public in this case, right, then the only classes that can use point2 are the ones that are in that exact package. Right? So if there's a class in basics, it wouldn't be able to use point2. If there was another package called geometry dot, I don't know, something, right, then classes in something would not be able to use the point2 class. Right? It's only the classes that are in the exact same package that can use the class. So for now, all of our classes should be public. Fields can have one of four access modifiers. Private means the field is visible only inside the class that it's defined in. Right? No access modifier is package private, so classes inside the same package can access the fields directly by name. Protected we'll look at several weeks from now. And public means that the field is visible to every class everywhere. Right? So if you have a public field, sorry, let's back up here. So if x and y were both public, then someone can make a point2 object called p, and then they can write p.x equals something and p.y equals something. Right? So that gives you public fields give other classes direct access to the fields. Okay, so a safe rule of thumb. Right? If you have a field that represents a constant and you want other people to be able to use that constant, make it public. Right? So pi, the field that represents the mathematical value of pi, is a public field in the class math. Right? Otherwise, you should probably make your fields private. Right? Occasionally, so later on in the course, we'll consider using what are called protected fields. So these are used when you are implementing an inheritance hierarchy. All right, so there's the beginning of point2, right? So we've got a class called point2. It's got two fields, x and y. So let's try this exercise again with another simple class. All right, so I want to implement this counter class. And the counter is just something that counts in increments of 1, starting from 0. Right? So it counts 0, 1, 2, 3, 4, up to the largest integer value. Right? Oh, sorry, that should be what fields do you need to represent a counter. Right? So what fields do you need to represent a counter? Well, if I'm just keeping a count, all I need is an integer field to keep the count. Right? So once again, right, here's our package. Whoa, sorry. There's our package. Right? Here's our class. It's public, right, called counter with a big C. Right? It's got one field, the value of the counter. Right? And that's it. It's also private. Right? So only the counter class itself can see that field. Okay, so now I want to implement a stopwatch. So this one's considerably harder than the previous two. Right? So I want to implement a class that represents a stopwatch where the user can start or stop the watch. Right? If they ask the stopwatch for how much time has elapsed right, then the stopwatch can tell them how much time has elapsed since they pressed start. Right? If they press start, then stop, and the user asks how much time, and the user asks the stopwatch how much time has elapsed, it tells the user how much time has elapsed between pressing start and stop. Right? And so now you have to, now when you try to implement this thing, it becomes quite a bit harder. Right? Which is why there's question mark, question mark, question mark here. Okay, so to implement this thing, you need to know how you can get time from the computer. So there's a method called nanotime in the class system. Right? So nanotime gives you the most precise available system timer in nanoseconds, right? So 10 to the minus 9 seconds, relative to some fixed but arbitrary time. Right? So in other words, nanotime returns some integer value that represents the time. Right? So if you want to compute how much time has elapsed between a start and stop time, right, then what you do is you call nanotime when you start the watch, and you call nanotime when you stop the watch. Right? You can then compute the amount of time that's elapsed by taking the stop time minus the start time. Right? And that will be in nanoseconds. Okay, so what do I need? I need a start time and a stop time. Right? So I'm going to call that raw start time because it's in nanoseconds and I want seconds on this stopwatch. Right? Nanotime returns a long, right? So an integer value that's represented using 64 bits. I have a stop time, right? So that's the, again, that's going to be a value that I get from nanotime, and it's also a long, right? And now I need to know, is the watch running or not, right? Because you can start the watch and then it starts running, right? If someone asks how much time has elapsed, you want to tell them how much time has elapsed since you pressed start, right? If you stop the watch and someone asks you how much time has elapsed, you want to tell them how much time elapsed between pressing start and stop, right? So you need to know, is the watch running or not, right? So here I'm just going to use a Boolean field to represent that, right? True if it's running, false if it's not. Okay, so we've got 3 classes now. They're all relatively simple. Can we actually use the classes in the form that they are in right now? And the answer is surprisingly yes. You can in fact use them. Right? So if you create this little program, you can actually make a point2 object. Right? Now remember what point2 looks like. Right? That's all that point2 looks like. Right? We got a class declaration and we've got 2 fields. There's no methods, there's no constructors. Right? But you can go ahead and make a point2 object using new. Right? So you can write point2 p equals new point2, and that works. Right? Counter is similar. Right? All we have is the class, declaration, and a field. Right? No constructors, no methods. But you can write new counter, and that works. And similarly with stopwatch. Right? You can write new stopwatch, and that also compiles cleanly. Right? So all of these code examples will work, which is strange because we haven't made a constructor yet, but it looks like we can still use one. All right, so remember one of the pillars of the object model is this thing called encapsulation. Right? So I can add features to our classes to make them more useful. Right? So far we've got, what do we got? Our classes are encapsulating some fields, and that's all that they're doing right now. Right? It would be nice if we could actually use the objects to do something. Right? So it would be nice if I could use a counter to count. It would be nice if I could use a point2 object to represent a point and move it around or something like that. It would be nice if I could use a stopwatch to actually tell me how much time has elapsed since I pressed start. Right? And so when we, to add features to the class, we want to add constructors and methods to the class. Right? So this term encapsulation in object-oriented programming means the bundling of data, so fields, right, and methods that use the data and turn it into a single cohesive unit. Right? So to begin with, we want to start by creating some constructors. So the purpose of a constructor is to initialize the state of an object. Right? So in other words, the constructor should set the fields of an object to some reasonable values. Right? So remember that. Right? That is the purpose of a constructor. right? If you don't call a constructor, so if you make a variable of a reference type and you don't use new in a constructor, you don't have an object, right? The constructor in combination with new is the thing that makes an object. Okay. So to make a constructor, what you do is you create what looks like a method. The method, what looks like a method, has the same name as the class. Right? It never returns a value, not even void. Right? And your constructors are allowed to have 0 or more parameters. Right? So the constructor with no parameters is called the no argument constructor. So it's the one I used a few slides ago. Right? That's calling the no argument constructor, as is that and that. Right? No argument constructor because there's no arguments. Right? Notice the name of the constructor is the name, same as the name of the class. Right? Okay, now why does this slide work? Right? We haven't defined a constructor in any of our classes, but if you compile this program, it actually will run. So in Java, if your class defines no constructors, then the Java compiler automatically makes one for you. Right? So it silently inserts a no argument constructor for you. Right? So the compiler generated no argument constructor will go in and set your fields to some default values. I don't remember if I tell you anywhere what it does. So the no argument constructor for stopwatch will set the start time, the stop time to 0. Right? So for any numeric fields, primitive numeric fields, they all get set to 0. Right? It'll set is running to false. So any primitive Boolean field will get set to, its default value becomes false. For any reference type, the default value is null, right? Which we don't have in this case in any of our examples. Oh, it's right here, sorry. Okay, so the no argument constructor has 0 parameters. And it's supposed to initialize the state of an object to some well-defined default value. Now, if you're going to implement a no argument constructor, you get to choose what the default values are. Right? The compiler generated no argument constructor initializes all numeric fields to 0, Boolean fields to false, and reference types to null. Right? So for the point 2 no argument constructor, we get to decide what are we going to set the points of what are we going to set the coordinates of the point 2. Right, and so this is when you go to implement the no argument constructor, you have to ask yourself what is a sensible default point. Right, so you can argue for many different default points. Right, 0, 0 is probably the most sensible default point that you can come up with. Right. So can we implement the no argument constructor ourselves? The answer is yes. Right, constructor name is point 2. Right? There's no return value here, right? So it's not a method. It's a no argument constructor, so there's nothing inside the round brackets. Right? Our constructor is public, which means that any other class can use this constructor. Right? Okay, so what is this constructor supposed to do? It's supposed to set the value of x and y. And so the syntax I'm using here is this.x equals 0 and this.y equals 0. Right? So inside a constructor, the keyword this is a reference to the object that's currently being initialized. Right? A constructor has access, so constructors can have an access modifier. Right? So the possible access modifiers are the same as the access modifiers for fields. Right? So that can be public, protected, private, or no access modifier. Right? And the meanings are the same. Do I have an example here? Okay, so I'm going to explain right now what this .x means and this .y means. Right? So when you make a new point 2 object by using new and calling a constructor, right? What happens is, right, a reference variable called p gets created somewhere in memory. Right? So we have point 2 p equals new point 2. So p pops up somewhere in memory. New allocates object for a point 2 object. Sorry, new allocates memory for a point 2 object. Right? The way it does this is it copies the point 2 class, plunks it down somewhere in memory. Right? So we've got a copy of the point 2 class, and it gets dropped somewhere into memory. Right? Now, in the point2 class, we've got two fields, x and y. They're not static. And so what that means is that the object that was created gets its own fields called x and y. Right? Now the constructor starts to run. Right? So the constructor, when the constructor runs, right, it needs to know what object is it initializing. Right? So there's your point2 constructor running somewhere in memory. Right? So whenever you run a method or a constructor, that thing has to run somewhere in memory. Right? So the point2 constructor appears somewhere in memory, and now it starts to run. Right? The problem in the point2 constructor is it doesn't know what the point2 object is that it's trying to fill in. Right? It doesn't know, or it needs some way to know. It needs to fill in the fields of that object that's right there. Right? And so the way it works in Java is every constructor automatically gets a parameter called this. Right? And the value of this automatically gets filled in with the address of the object that was created by new. Right? So the constructor starts to run, it gets a parameter called this, its value is 600A. Right? So now the constructor knows, oh, I have to fill in the object at address 600. Right? So when you say this.x, right, this is just a variable. Right? So this is just a reference. Right? What does this refer to? It refers to the object here. So what is this.x? Well, this.x is that value there. Right? So that gets filled in with 0 and 0. Right? This.y, right? This, so that's the object at address 600, so come up to here. Does it have a field called y? The answer is yes. So this.y gets assigned the value 0. Right? And so that's what the parameter this means in Java. In Python, I think you typically use self. Right? So if you guys did some object-oriented programming in Python, then they would have told you about this parameter called self. Right? But in Python, you have to put the parameter in yourself. Right? So every Python method or constructor has a parameter in it, has a parameter called self. In Java, you don't create the parameter yourself. It gets created for you automatically, and it's called this. Right? So that's what's going on when you actually make an object in Java. In Java. Right? There's actually a whole bunch of stuff that happens. Okay, any questions about what this means? Anybody? All right. Oh, finally, the last thing that happens is the value of p, right, gets set to the address of the newly created and initialized object. Right? So now p is a reference to the object at address 600. Right? So now when you say p.someMethod, right, p.someMethod, so it knows to call the method using that object right there. Okay, what about the counter class? So I want to make a no argument constructor for the counter. What should I initialize the counter to? Well, you probably want to start counting from 0. So that's easy. Right? It's just this.value equals 0. Right? One more time. I'm just going to go through this slide very quickly. Right? When we call the constructor, when we make a variable and call the constructor, the variable appears in memory. Right? New allocates memory for the counter, so it copies the counter class, plunks down the copy somewhere in memory. There it is. Right? So every counter has its own value field. Right? The counter constructor runs. Right? So it appears somewhere in memory. It gets a parameter called this. Right? The value of this is the address of the object that was just created by new. Right? Constructor runs. In this case, it sets this.value to 0. Right? So what's this? Well, this is the object at address 550. So up we go to here. Right? What's this.value? Well, it's that value there. So we set that to 0. Right? Finally, the constructor finishes running, and so now we can fill in the value for C, which is just the address of the newly created and constructed object. Right? For the stopwatch, it's not clear really what to set the start and stop time to, because nanotime's funny. So nanotime doesn't say that the time starts from 0. Right? If you read the documentation for the class or for the method, it says the start time could be anything. Right? So here I'm just going to set the start time to 0 and the start and stop time to 0, and the watches will not be running. Right? So that's pretty straightforward. Right? So this.raw start time gets 0, gets the value 0. the stop time gets the value 0, and is running gets the value false. Right? Now, one of the questions we often get asked, right, by people new to the language is, do I always have to write this? Right? So in other words, if I just wrote raw start time equals 0, would it work? And the answer is yes, it would work. Right? On the slides and in the notes, I always write in this dot, right, to indicate that we're actually accessing a field here. Right? And so I will always write this dot in front of a field, access, but it turns out you don't have to, except in some circumstances, which I will show you later on. Okay, so we've got our constructor. We have one constructor now for each class, right? What about some methods? So a method is something that just performs some sort of computation, right? Now, all of the methods we've implemented so far have been static, right? So in assignments 1 and 2, right, you've got classes, everything's static inside those classes, right? In today's lecture, stuff has started to change, right? Our fields are not static. Right? Constructors are never static, right? And now we're going to implement methods that aren't static, right? So when you make a method and it's not static, that method is allowed to access any field, any field belonging to an object, right? So for example, I can provide a method that allows the user to set the x and y coordinates of a point, right? So inside the point2 class, right, I'm going to create a method called set. Right? Set takes in a new x and a new y coordinate. So when you call this method, so when someone writes p.set, where p is a point reference, right, they're asking you to change the coordinates of the point referenced by p to new x and new y. Right? So how do I change the x and y coordinate of the point? So it turns out you write this dot x equals new x, and this dot y equals new y. Right? Do I explain where? Okay. Right. So what does this mean inside of a method? Right. So inside of a method, this is the reference to the object that was used to call the method. Right. So if I were to write somewhere in a piece of code, p.set, right, new x, new y, right, then inside the method, this is the same as p, right? So in other words, it's the point that you used to call the method, right? Or another way to think about it is it's the coordinates of the point that are being changed. It's the address of the point that's being changed, right? Right. Now, whatever you do, don't flip this backwards, right? So it's very, very common to see students write new x equals this dot x and new y equals this dot y, right? But that doesn't make any sense, right? New x equals this dot x means you're going to change new x to be equal to the x coordinate of this point, right? Which is exactly the opposite of what you want to do. Okay, this is a bit funny. So set returns a point2 reference, right? Which is odd. So I'm returning a reference to a point2 object, right? And so I'm going to return this in this particular method, right? And you might ask, well, this is weird. Why would I return a reference to the point that I just used? So what this lets you do, I have to edit a slide, sorry. So somewhere else. So not in the class, right? Somewhere else, right? If you return a reference to the point that was just changed, then you're allowed to write stuff like this. p.set, so 1, 1, dot, something else, some other method. Oop, like that. Okay, so because set returns a reference to the point that was just used to change, whose coordinates were just changed, right? In this little piece of code down here, right? So p.set, right? That actually returns a reference to p, right? So you can now use that reference and call some other method, right? Which turns out to be really handy when you're working with mathematical entities, because when you start to add stuff together, so if I wanted to add p, q, and z or p, q, and r together, right? I could go p.add q.add r, right? And I don't have to do them all on separate lines, right? If this didn't return a reference, so if it returned a void, for example, right? Here I'd have to write p set 1, 1, and then on the next line I'd have to write p dot some other method. So returning a reference to the point that was just changed, in this case, is useful, right? It's not always useful, but in this case, it turns out to be very useful. Okay, we can add other methods to the class. So I can add a method that lets the client set just the x coordinate of the point. Right? So here's a method, oops, sorry, just the y, just the x. Right? So here's a method called x. Right? It takes in a new x coordinate, and it changes the x coordinate of the point. How do you change the x coordinate of the point? Well, it's this dot x equals new x. Right? And just like in the previous example, I'm going to return a reference to the point that was just changed so that I can chain other method calls all together. Right? You can do the same thing for y. So this dot y equals new y. Right? And so on, and so on, and so on. Right? Okay. So methods that change the state of an object are called mutator methods. Right? So anything that changes a field belonging to an object is a mutator method. Right? So set x that takes in a parameter and y that takes in a parameter, these are all examples of mutator methods. Right? They change the state of some object. Accessor methods are methods that return information about an object. They don't change the state. Right? So for example, if I have a point, the user might want to know what is the x and y coordinate of that point. Right? So I can provide an accessor method that returns the x coordinate. I can provide an accessor method that returns the y coordinate. Right? So here's a method called x. No parameter this time. Right? It returns a double. Right? And what does it return? It returns the x coordinate of the point. Right? So what's the x coordinate of the point? Well, it's just this dot x. Right? Return the y coordinate of the point. Okay, what's the y coordinate of the point? Well, it's just this dot y. Right? I guess that would be a good place to stop. So we'll take apart these method headers in the next class. And then continue on with other constructors and so on and so forth.